Hello everybody. Today I'll be showing you how I reverse engineered uh, an error producing assembly code where I was only given the machine code in terms of hex codes, and I was able to reverse engineer this into assembly instructions and find out the problem in the logic. So first of all, I had these instructions. I converted them into binary, so it would be turned into a decodable format, as I've mentioned here. Then I know that for every single instruction, no matter what kind of instruction they are, the first 6 bits represent the condition, which is 4 bits, and the opcode, which is 2 bits fields. And I separated the whole binary instruction into 3 parts: the count field, the op field, and the rest. I did for this for all of the instructions, and then I noticed some patterns, right? Whenever it's 1110, it's always done. So I went through all of them, and I noticed that some instructions had this 1011. I looked up to the table, and it said it's less than. So this means this instruction is going to be executed whenever the NZCV values agree with the less than condition. And when I looked at the second part, I was able to notice the instruction types. So this is a data processing instruction because it's both 0. Same for this, up until here, where it is actually a branching instruction because it's 1 0 and 0 1 here, which is a memory instruction. So because I was able to deduce the main facts, I knew how to decode the rest. Because you can see that for like branching instruction and a data processing instruction, these bits are decoded completely differently. And we need to know this part to be able to decode the rest. So because this is a data processing instruction, um, so in data processing instructions, there are a few exceptions where the formatting doesn't match the others. It's multiply and shift. So in multiply, we basically have hard-coded bits towards the end as 1001, and none of these instructions had that. For shift, the immediate value is 0, and there is a hard-coded bit, but none of those had that. Not a hard-coded bit. So a hard-coded register. It's more like this register was zeroed out, and we used the register inside the source2 field for the shift command. And this is for shift only, not shift combined with other instructions. So once I ruled them out, I was able to decode them really easily because I had only 3 variations of data processing instructions. There was one, when the immediate was 1. So when immediate is 1, the instruction is basically, the source2 field is basically 4 fields of rotation and 8 fields of just raw value that you rotate. And then for values when it's 0, you look at the hard-coded bits. So if the bit 4, this bit is 0, then that means that is an immediate shifted register. If that's 1, that means it's a register shifted register. Considering that, I was able to decode the rest. So most of them goes like this. This is I, the command. So I also looked up the command codes. This was sub, this was add, and S, whether it's gonna change the NZCV registers or not, bytes or not, to be more exact. And this one is RN, this one is RD, this one is shift amount in 5 bits. This is the shift bits to be more exact. So it looks there are 4 variations of shift commands, and it looks at this and decides which one to choose. There is this hard-coded bit, especially for this register shift, uh, immediate shifted register, and this is the RM, the third register, the second source register. So I did this for all of them, and then I encountered. I'll go with memory first because it's closer to the structure. Then I did the memory one. In memory, you have I, P, U, B, W, L bits. And based on the combinations, I was able to decide whether it's offset, prefix, postfix, and whether it's byte, store, load, and those things. And whether it's positive or negative. I noted all of them down, like as such, and this helped me identify the assembly code. So basically, and I also did this for branching. Branching is a little different because branching is expressed from the PC relative branching, right? It looks at the current PC plus 8, because when the microarchitecture accesses PC, it gets PC plus 8. So it's like this shows -7, and it's 2 instructions below, right? So it means -5 from this instruction. I went 5 steps back, and here I added a branch. I added the same here, and yeah, I was basically done with this. And just a note, the branching instructions are really simple. It's just we discussed these. This is 1, always hard-coded as 1. The second bit is whether it's link or not. So for example, we had 1 here, which means this was branch with link. I think I forgot about adding L here. Good thing I noticed. Yeah, branch with link, and yeah, this is how I did it. And it's really easy from this point on because you already know every step. You know it's a data processing instruction and sub. I didn't even have to mention this, but I noted everything down. With register, these are the registers. This is the source 2 register. I should have done RM here, but that's still alright. And then everything was done. And I did a quick check on CPU later. I took a screenshot here, and I checked whether these instructions actually match. And it turns out they do. So I finally constructed the code with the comments, and here's the code. Let's work on it now. So basically, it sets up a few values. R1 is for nothing. It's not really used for nothing. It's not really used for anything. R2 is an increment value, so how much a variable increases every loop. R3 is our initialization variable. It's our counter. R4 is our limit, so here we do while I is less than 5. Show this as sub. I would recommend CMP though, but to not mess up the functionality, I kept it as such. This is not actually updated version, but yeah. So while I is less than 5, increment R0 by 10, by the value of R2, which is 10. So every time the loop repeats, the value of R0 is incremented by 10. And because this is I is less than 5 and start from 0, it's going to be repeated 5 times, and the result is going to be 50. R0 is going to be 50. And then, yeah, we do this while I is less than 5, repeat the loop, nothing important here. But after this, when the thing ends, when this branch ends, it branches to another one with link, which is really intriguing. So they have a push of the LR, alright, then they set up a few variables. They add those variables and store that in R6. And then they have a condition or some sorts. It has an S, so we naturally deduce that it's a condition, but it's not actually used. And then branch is repeated again. And there's a problem with this. The problem is, first of all, the most obvious one is that branch is always done, no matter what's. It's an infinite loop. And you know what happens when you push something to the stack every time and don't stop the loop at all? The stack overflows because it's filled and never um, emptied. So my solution involved this. I looked at the parts of the problem. Nothing was wrong here, but R0 wasn't set to 0, which was a problem for repeated runs. Um, then here everything was fine, and BL was used, so it's a function, right? And I think it should be a function because they did something with the link register, and you wouldn't do that unless that's a function. It seems like here the user forgot to pop the link register, and they also did an unconditional loopback, and they also use like they did this without using it. So I think it was some like part of the code was lost. So in my final code, I added this field, which is basically to reset R0 every time we run, just for convenience. And I'll talk about this part later. So the loop stayed the complete the same. It links to the function. I changed the names, right? By the way, I didn't save any callee saved registers or caller saved registers because this code does not follow the conventions. R0 is usually used for the first input, R1 is used for second, then R0 is used for output, but I didn't see the code following any of these, so I just disabled the function covered callee saved register settings in CPU later to just avoid an error. And I'll also show how recursion works in this example. So I just decided not to save any of these because they're not gonna matter in the end. So some functionality is just a bunch of random instructions that work together. So I changed this push LR just to make it simpler and easier on the eyes. Um, this was kept the same. this was kept the same. But because we had an S here, I thought, why don't we add some conditional codes here? So I thought every time we're inside a new loop, we add 1 to R3. So we'd stop the recursive part and would, yeah, I talked about this, and would branch to the function when it's less than. So when the value, when R3 is equal to R4, it would completely stop repeating itself, and it would like branch back and finally empty the stack by popping LR and BXLR. So which means that just go back where you started, and in the end it will go back here, right? And uh, I don't want the program to repeat this once again, because it would if I didn't have anything here. So I added branch to end and ended the program. So yeah, let's see this in practice. We first start from R0 or 1. Yeah, these values, we set them, and yeah, we start the loop. Uh, Loop is pretty self-explanatory. While I is less than 5, we'll increase um, a value by 10. Let's see how the value changes. So we're adding it to R0. Look at R0. It should be 50 after the loop, or 40. Yeah, 50. Um, then skips all of them. It branches to the function. It pushes something to the link register. And notice that I disabled this field. Yeah, you see the stack pointer is changed. Now we move these values, we add them. This is nothing important about it. It doesn't do anything that affects the rest of the code. It's just some calculations. So let's look at R5 now. See, R5 is now -10. We add 1 to it. R3, so when we subtract, the value is less. I mean, more than the previous one. So we repeat this, and now it's -9. Now it's -8. Now it's -7. So this is like a recursive loop going on. It's going on, it's going on, it's going on until we reach 0. So it's now -1, and it should be 0 now. And this, it's gonna skip this part. It's going to pop the link register, branch back, pop it, branch back, pop it, branch back, pop it, branch back, until we do it enough times, and the program ends. I went too far, I guess. So yeah, anyways. This is how the program works. And so basically this program had no good logic. I mean, nothing functional with it. It's just a random bunch of instructions. I don't think it had like any goal. But now I converted this instruction to something that does a loop, that does a function, and inside a function it does recursive calls. It uses the link register. It yeah, uh, it pushes that onto the stack, pops it from the stack. I mean, there's everything we learned. I combined this into one program, and I hope you learned a lot from this process. Learned about how instructions work and how a program is actually implemented inside the CPU. We didn't talk a lot about that part, but it's still important to understand how something that a person sees and understands is converted to something that a computer sees and understands. And by the way, if you noticed, um, I use this syntax here, where you normally have to add three registers here, but I added two. And the reason for that is because assembler automatically understands my intent, converts this into something more semantically similar to what I meant. I meant that add the value of R2 to R0 and store it there. It's normally done as such, but the assembler, which is quite clever, automatically converts this into this, where there are three fields, three registers. And thereby it allows me to express my intent and communicate to the computer at the same time.